Okay, I'm going to try to work through these sample questions fairly quickly. I'm going to try to add what I can to the ideas, but there's a lot here for you guys to get through. So one of the classic skills for your lines, one of those skills you really need to make sure you have, is the given a pair of points, you want to be able to make a line between them. So we're given 2, 5, and 4, -1. So I'm just going to put here 2, 5, and 4, -1. You may remember I suggested at one point for your back in chapter 2, labeling these. Label them x1, y1, x2, y2. It just takes a moment, and it helps you not switch things and make some of the sign errors that are common. So if we're going to make a line, we want to find the slope of that line. You may remember slope of a line, y2 minus y1 over x2 minus x1. So now that we have them labeled, we can just plug them in. So -1 minus 5 over x2 is the 4 minus 2. So a nice -6 over 2. So our slope is a fairly straightforward -3. How you want to build the actual line is up to you. There are a couple different skills. I like using y equals m x minus x1 plus y1. Sometimes you see this over here with a minus y1 as the point slope form. Some people just like using slope intercept form straight. Whatever makes you happy, whichever skill you like to use. So y equals -3x minus my x1 was 2 plus y1, my y1 was 5, and then just simplify. So y equals -3x plus 6 plus 5. So y equals -3x plus 11. So that's your line in slope intercept form that passes through that point. So that's part A. Part B asks you to build the equation of a line perpendicular to the line in part A. So part A has a slope of -3. So to be perpendicular, we need to have the negative reciprocal. So the -3 is going to turn into a positive, and we're going to look at its reciprocal. Sorry. So any line with this slope is going to be perpendicular to our line in part A. Well, that's all we were asked, to make sure we are a line that is perpendicular to a line in part A. So y equals 1/3 x plus anything will be perpendicular because the slopes will be negative reciprocals of each other. We could put +5, +7, +8, or just leave it as +0. It doesn't matter what the b is. I'm going to say plus pi. It doesn't matter what this is, as long as it has the negative reciprocal slope, it's going to be perpendicular. Part C is a little more specific. We want to be parallel, means it has the same slope to part A, and passing through the point 6, 1. So the slope of our original line here in A was, again, -3. So the slope of our our parallel, is going to still be -3. And we want to pass through the point 6, 1. So this is just, we've been given a slope, we've been given a point, make a line. Here we were given a pair of points and had to figure the slope. Once we had the slope, we took the slope and a point, and made the line. Here the slope we want is told by the perpendicular, but once you have a slope and a point, you can make a line. I'm going to use the same form here, but again, use whichever form you're most comfortable with. So y equals -3x minus the x value of the point I want plus the y value of the point we want. So -3x plus 18 plus 1, so y equals -3x plus 19. If this perpendicular one had also given us a point to go through, we'd have used that point and done the same thing. The big difference here is it just wanted anything perpendicular. Here it wanted a particular parallel. If this had been reversed and it said give me a line that's parallel to the line in part A, then we'd have done the same thing. It would have been y equals negative 3x plus anything. But it had to go through this point, so we had to use that point to build our line. Okay, that's number one. Number two, we want to show whether or not f of x equal to 4x minus 1 over 2 plus 3 and g of x equal to 2x minus 5 over 4 to show are they inverses and to fully support your answer. Stresses fully support. The only way to truly support whether two things are inverses or not are to find the composition in one direction, find the composition in the other direction, and show that they are both equal to x. So, for example, if we want to take f and compose it with g, find that new function of x. That's f with g inside of it. G is 2x minus 5 over 4, so that's what g is. So that's what's going to go into f. So f is 4 times its input. The input is this whole mess, so 4 times 2x minus 5 over 4 minus 1 over 2 plus 3. Simplify this, and we should, if they are inverses, we should be left only with an x value. Nice thing is the 4's cancel there, so we get a 2x minus 5 minus 1 over 2 plus 3. Sorry, it's hard to see that at the bottom there. Over 2. So combine our like terms there. So 2x minus 6 over 2 plus 3. Make sure the 2 divides into both of them. X minus 2, minus 3. Plus 3, those undo each other, and we get identically x. That is not sufficient to show that they are inverses. We'd also need to show, f composed with g and g composed with f. We have to show it in both directions. So we've shown that f composed with g is equal to x. We'd have to similarly show that g composed with f in the other direction still makes x. And it does in this case. You should check that. On the tests, you'll want to show me both compositions. But for our context, it's actually fairly rare for one to work and not the other. There are applications in which it does, so you want to make sure you're testing both. But usually if one works, the other will. But do make sure you show me both of them. Since they both equal identically x, you want to give me your interpretation. So you definitely want to say, let's see, you were asked, are they inverses? So the answer to that question is yes. F and G are inverses. Be sure you answer that. The answer to this question is not x and x. The answer to the question, are they inverses, is yes, they are inverses. By the way, if you find that one of these doesn't work, like if this wasn't x, if this ended up being x plus 5 or something, you don't have to check the other one. If one of them doesn't work, it doesn't matter what the other one does. They both have to be x for them to be inverses. Okay, so that's 2. Apparently there's no question 3. Good. Question 4, given a function f of x equals 2x plus 3 over 5, that's a 3, that's a pen. We want to construct f inverse. Now this is quite a different skill from the testing whether or not two things are inverses. If you're asked to test if two things are inverses, you must show the composition in both directions. Do not use the construction tool to test inverses. It is not sufficiently robust. There are lots of problems with it. So if you're asked to test, show the compositions. If you're asked to build, we can use our solving tools. The nice thing about constructing inverses is really you've been constructing inverses for a long time. Every time you solve something, you're making an inverse. So to build an inverse, we're going to set it as y equals instead of f of x, and that's really just for our own notational simplicity. There's no real notational purpose for that as long as you're careful. And then, because the inverse takes our range and turns it into our domain and turns our domain into our range, we're going to switch our range and domain symbols. So part 2, switch x and y. As soon as you do that, you've really built the inverse relationship. If you left this as f of x, this would be f inverse right here. The only difference is we'd really like this to be solved for y. So everything else, or almost everything else, is solving this for y. So multiply your 5 over 5x equals 2y plus 6 when you distribute. Subtract the 6, 5x minus 6, divide the 2 equals y. So that's your solve for y. I know I did that quick, and if you wrote 5 half x minus 3, fine, same thing. The last part, part 4, this really was a question in function notation. This is an answer, but it is an answer in equation notation. We really want to put it back into function notation, so be sure you do that. Again, this is all about the solving technique. Every time you're solving, you're undoing operations. And inverses are all about undoing operations. So every time you solve something, you're undoing those operations, and you're undoing it in the right order. So it's just dependent on your solving. Again, be careful. This is a nice skill, but it is not sufficiently robust to test inverses. If you're testing inverses, use the composition. If not, if you're just building an inverse, this is a great tool for building inverses. Okay, number 5, solve. So we're solving x to the 4th minus 6x to the 3rd plus 22x squared equals 30x minus 13. Okay, that's certainly a big polynomial equation. Now be careful, we had a whole section, chapter 4, lots of chapter 4 was on factoring and manipulating polynomials. All of those polynomial manipulation tools really are so we can solve things like this. Anytime you're trying to solve a nice robust polynomial, particularly of high degree, do the same thing you would do with a quadratic. If it was a quadratic, you would set it equal to 0, and you would try to factor it. Now with a quadratic, if you couldn't factor it, a quadratic formula would work. This is not a quadratic, so we have to be able to factor it. Luckily, we have some nice tools to be able to factor it. Different ones you may remember, depending on whether you're looking at the book or some of the notes. You looked at, I tended to like b over a, where b were factors of the constant and a were factors of the lead coefficient. The nice thing about this problem is your constant only has 1 and 13 as factors, though of course they could be positive or negative. And the a only has 1 as a factor, so plus or minus 1. So you really only have a couple of possible rational zeros. You've got plus or minus 1, and you have plus or minus 13. Now, which one of those might you want to check? You could look at the graph and decide which one you want to check. But, the plus or minus 1 are sufficiently handy that we might just want to check those. But do look over your notes, look over your samples for chapter 4. Make sure you remember the robust versions of this skill. It is our skill for solving higher degree polynomials. So 1 and negative 1 are good things that might work. So look at the graph and check. But we're just going to check those here. So I'm going to try a 1 using the synthetic division to see if it's a root. I do have to make sure I have everything. This is a 4th degree, so that's 4th, 3rd, 2nd, 1st constant. Remember, if there are ones missing, we have to make sure the zeros are in there. And then perform your synthetic division. So 1, 1, negative 5, negative 5, what is it, 17, 17, negative 13, negative 13. Oh, that's nice. 0. So we know that x minus 1 must be a factor, and thus 1 is one of our solutions. Great. How many solutions do we expect, though? It's a 4th degree, so we should have 4. Some of them might be complex numbers. We're responsible for those as well. But we at least found one real number, 1. Now we could check positive or negative 13 now, but I'd like to just see if negative 1 works. So remember, I'm going to do it on the result here to keep breaking this down. So 1, negative 1 is what? Negative 6. Negative 1 times negative 6 is 6. And that's what? 23. That's going to be negative 23. So that's not going to work. Okay, so not that. So was that right? Yeah, probably. So let's try 13. Bring down the 1. That turns into a 13. Negative 5 and 13. There's negative 5, 13, 8. So 3 times 8 is 24. Now I'm not liking that one either. Now once you make this much of a mess, I'm going to bring down my 1, negative 5, 17, and negative 13. Now something you always want to keep in mind with synthetic division is just because 1 worked once doesn't mean you can't try it again. And the negative 1 didn't work, and the 13 started to get a little wacky. So I'm going to try 1 again. So 1, 1, negative 4. Oh, what is that? Well, negative 4. 13. 13. Oh, that's nice. So negative 1 works twice. So we know it's not just x minus 1, it's x minus 1 squared. So we have a multiplicity of 2 on our 0 of 1. And the nice thing is we're now left with a quadratic. So we now have x squared minus 4x plus 13 equals 0. This is a quadratic we can solve with the quadratic formula if it's not nice and factorable, which it's not. Quadratic formula. And that quadratic formula will give you your other 2 solutions. So you'll have x equals 1 with multiplicity 2, and you'll have the other 2 solutions that the quadratic formula gives you. And those might be real and irrational. Those might be real and irrational, or they might be complex numbers, whatever they happen to be. Now I did say we have to have 4 answers, and this kind of looks like it'll be 3 answers, but remember this answer has a multiplicity of 2 because it came up twice. So that'll be 1, 2, 3, 4 answers, just like they're supposed to be. Okay, so that was 5. How are we doing on time here? 17. That's not bad. So that was number 5. Number 6, I moved around, so we're at 7. So 7 and 8. Logarithms, Logarithms and exponentials. The biggest and most important thing you can ever understand about logarithms and exponents is that logarithms and exponents are the same thing. The same way addition has subtraction, the same way multiplication has division, the same way powers have roots, exponentials have logarithms. So anytime you see any logarithmic expression, even something as nice as log base 2 of 8, log base 2 of 8 asks an exponential question. 2 to what power makes 8? Well, 2 to the 3rd power makes 8. Log base 2 of 8 equals 3. Fundamental statement. Because 2 to the 3rd equals 8. Again, logs ask the question, what power on 2 makes an 8? Well, 2 to the 3rd makes an 8. So the logarithm must give us a 3. This is a nice pairing to remember. If you can remember these 2 sets of equations, you can remember your relationship between logarithms and exponents. Do keep in mind this is the same thing as saying, hey, if x divided by 6 divided by 3 equals 2 because 6 equals 2 times 3. This is the same kind of pairing that this is. This is true because this is true. This division is defined based on this multiplication. The logarithm is defined based on the exponential. So when we see w is equal 8 to the t and told to write this as a logarithm, well, the base of the exponent is an 8, so the base of the log must be an 8. All logarithms equal the exponent, So this had better equal the t, and it better operate on the w. I often visualize this 8 kind of swinging under and becoming the log, the same way the 3 swings to the other side when it becomes multiplication, or swings back when it becomes division. Here, this is a common log. Call it a common log because we don't see a base. Whenever we don't see a base, that base is always assumed to be 10. Called the common log because it is the base of our common counting system. We have a base 10 counting system. So just like the base of the exponent became the base of the log, this is a log base 10, so it's going to turn into an exponent base 10 problem. Log base 10 becomes exponent base 10. Exponent base 10 becomes log base 10. Log base 2 became exponent base 2. Dividing by 3 became multiplying by 3. Same kind of relationship. Technically, this is done. This is in exponential form. Don't write this as x equals 1,000. It's certainly true, but the question asked, write it in exponential form. This is the exponential form of this logarithm. If, by the way, it had said, if it had said the natural log of w equals, I don't know, v. Remember, the natural log is just like all of your other logs. Its base is just e. So there's a little invisible e down there. This is the natural base because e is the natural constant. It's just a particularly important value. So the same way, the base of the log becomes the base of the exponent. So e to the v equals our argument. Remember, there's nothing really mechanically special about the natural log or the common log. The common log is given its common name because 10 is the base of our counting system. We don't write the 10 the same way when you have a square root. You don't write the 2. We assume it to be a 2. The natural logarithm is our probably most important logarithm because e is our most important exponent because it governs all continuous growth and change in our universe. That is not an overstatement. It really does. So it has kind of its own special notation. Log, natural base. But the mechanics on both your common log and your natural log are the same as any of your other logs. They just have slightly different symbology. You could literally write this as log base e of w equals v as the original problem. Then the e swings over w equals e to the v. Don't do that because I want you to be using the proper notation. But if you want to write it this way just as a step along the way because it helps you stay organized, do it. Great. Okay, for number 9, we will start video 2. These videos don't like to be more than about 20 minutes, so we'll make another video here